Now am I audible? Hmm. In that in this table, again the network is slow, I think. Are you able to am I audible, students?
Yes, ma'am.
But I am facing too many problems here. Again connecting. Is the screen visible now? Yes, is it?
Yes, ma'am.
Okay, so this was the table from which we proved that this is a closure group. Closure property gets satisfied because the composition table uh, uh, containing all these elements only means 1 minus 1 I and minus I. Okay. Then the next property, associativity. Multiplication operation itself is associative. So associativity is also proved there. Then next was identity. Okay. In multiplication, when we consider one is the identity element always, because one multiplied by any number, it gives that any number. Okay. So one is the identity element here. Then inverse property. For inverse property, what it is? From the composition table, we see that the inverse of elements of 1 minus 1 I minus I are 1 minus 1 minus I respectively. Here 1 inverse is 1, minus 1 inverse is minus 1, I inverse is minus I, and minus I inverse is I. Okay. So this is the case with inverse property also. So the inverse property also gets satisfied here. Then the last is commutativity. Then again, the corresponding rows and columns of the table are identical. Therefore, the binary operation product, that is this one dot is given there, means multiplication is commutative. We can see here all the rows and columns are in the same order. 1 minus 1 I minus I, 1 minus 1 I minus I. Okay, it is about first row, first column. If we consider second row, second column, what it is? Minus 1 1 minus I. Then it is also minus 1 1 minus I. Same we can consider with third row, third column, that is I minus 1 1. Same here, I minus 1 1. And for the fourth row, fourth column, it is minus I 1 minus 1. Here it is minus I 1 minus 1. Okay, so here the commutativity also gets satisfied. Hence, we can say that G multiplication is an abelian group. Here G is given like this, 1 minus 1 I minus I is an abelian group under multiplication. We have proved this with the help of this composition table. Okay, when such type of examples come, by deriving the composition table, we can solve all the satisfied all the properties, and then we can say that it is an abelian group. Okay, then the next part comes is the group codes. Okay, in group codes again, group codes are a type of code. Okay, in which group codes consist of n linear block codes, which are subgroups of G raised to n. Now, what is G? G is a finite abelian group. Okay, and it contains G raised to n uh, linear blocks. In this example, as we have seen, this is the finite abelian group. Finite means only 4 elements are there, and it is an abelian group. So here, group codes consist of n linear block codes, which are subgroups of G raised to n. G raised to n here is G is a finite abelian group, and n is n number of linear blocks are there. Okay, codes are like these one. Those are represented with matrices. Okay, and then a systematic group code C is a code over G raised to n. Okay, that code is denoted by C, and it is a code in between G raised to n. Means here G raised to n subgroups are there for abelian group, finite abelian group, and C is the code from that linear blocks. Okay, and those linear blocks are nothing but our matrices in 0 1 0 1 means binary matrices are there. In binary language, those matrices are defined. Okay, 0 1 0 1 like that. The remaining bits are information bits themselves. Means whichever is the bits there in the code, those are okay. Those are appended with the information bits. Okay, and group codes can be constructed by spatial generator matrices. Group codes can be constructed by spatial generator matrices. As I told you, these linear blocks are nothing but the matrices, spatial generator matrices. and this is used to construct these group codes. Okay, I have given you this link which contains means it is a YouTube link, and this guy has very effectively uh, shown us that how to derive the matrices. Okay, means how the group codes are generated. That is shown in this YouTube video. Okay, so you can refer this video, and you will see how to generate the group codes. Okay, uh, again it is showing me the unstable network. I don't know why. Actually it completes our seventh unit also, and if you wish to means I if you wish to show you these convergence, I will also show you. There is no problem, but in the next lecture. Okay. For now, means you can see this video, and you have already this PPT's link shared with you, so you can access this link also in your teaching diary. I have shared link of this unit 7, and I think on group also. In that it is there. This link is there, so you can see there. Okay. Uh, then so this groups chapter or groups unit is completed in this. We have seen all these uh, bits, polish expressions and their compilation, how the stacked data structure is used for that, that also we have seen. Then this is the compilation process for polish expressions. And after that, we started with groups are what? These are possessing these properties: closure, associativity, identity, and inverse. And for abelian groups, commutativity is also there. Then we have seen some of these laws here, and then we went for examples. These examples are very important, in that non-zero real numbers with respect to multiplication is a group, while with zero it is not a, means all real numbers set R is not a group. But if zero is not there in the real number set, then it is a group. Then we saw one example of semi-group and monoid also, in which semi-group is what? Again, it is possessing only two properties, that is closure and associativity. And if it is possessing identity property, then it is a monoid. Okay. Then we again seen this example, like this one, uh, set of all positive rational numbers forms an abelian group, and